right, so let's continue on with our Chapter 6 lecture, which is about gravity, and move on to the next topic, which is circular orbits. So let's get into that. So, big picture, I want you to think about the general problem of a two-body orbit, meaning we have two massive objects, they're exerting gravitational forces on one another, and they're orbiting each other. Okay? So let's look in this animation that I'm about to play at 4 different cases. Right? In the first case, on the left, the two objects have the same exact mass. And then as we move to the right, there begins to be a bigger disparity between the masses, such that in the very final case, one object is really, really massive, and the other is really, really small in comparison. Okay, so we go from equal masses to a huge difference between the two masses. Okay? So it turns out, in a situation like this, when you have a two-body orbit, the two objects orbit around a common point, and that is called the center of mass of the system. Now, when we get to Chapter 9, we're going to actually talk about what the center of mass means and how to calculate it. We're not going to do that just yet, but let's take note of where on these pictures we have the center of mass. So it's given by this red cross, which is on each one of the pictures. So in the first case, we have two equal mass objects. These two masses are the same. Whenever that's the case, the center of mass is exactly midway between the two. Okay, so we have two equal mass objects. The center of mass is actually exactly halfway in between them. Now, if we go to the next one, this one is bigger, more massive than this one. So the center of mass is going to be closer to the bigger object. Okay? And then again, as we move over here, this is even bigger now. So the center of mass gets even closer to the big object. Now it's actually inside of the big object. And then again, just ramp up the difference between mass even more. Now the center of mass is almost right in the center of the bigger object. Okay? So what do these orbits look like when we play them out? Well, it's just what I said. Each one of these objects is orbiting the center of mass. Okay? So in the case of equal masses, they're both orbiting the center of mass, which is exactly halfway between them. They're still both orbiting the center of mass here. It's just now that the center of mass is closer to the big one than before. And then as we go to the very last case, where there's a really big difference between the two masses, it's almost as if, okay, it's approximately as if, the big object isn't moving. It's barely moving at all. It's just kind of wobbling around a little bit. And the small object is moving in a circle around it. Okay? So this is the situation we're going to be dealing with from here on out, where one object is totally dominant in terms of its mass. In other words, let's call this one big M, and let's call the smaller mass lowercase m. So we're dealing with a situation where big M is much, much bigger than little m, and the center of mass is almost right in the middle of big M. Okay? So when we're dealing with one body being much less massive than the other, we can basically treat it as if the smaller body is just moving in a circle around the center of the large body. Okay? It's not exactly true because the large body does move around a little bit, but we can treat it as if the large body is stationary and the small body is just moving around it. Okay? So that's what we'll do from here on out. And since we're dealing with circular orbits, let's do a review of circular motion because this is going to be highly relevant. So let's take a quick accounting of everything we learned way back in Chapter 5 when we first saw circular motion. Okay. So the one thing we found is that if something moves in a circle, even if its speed is constant and not changing, it still has acceleration. And the reason for that is it's changing its direction of motion constantly, so it must be accelerating. We call this centripetal acceleration, and the word centripetal just means seeking the center. So the acceleration is going to be pointing in towards the center of the circle that we're moving in, whereas our velocity is going to be tangent to the circle. So acceleration, velocity, A and V, are both shown here. Okay, we also took this a step further, thinking about the dynamics of circular motion, or the forces involved in circular motion. And for that, we use Newton's second law, which says that the net force acting on an object is equal to its mass times its acceleration. Well, if there's an acceleration, which points inwards. That also means there is a net force pointing inwards. So on our diagram, we'll show that the net force acting on this object points in towards the center of the circle. Okay, so typically what we do here is we apply Newton's second law to the radial direction, where the positive r direction is going in towards the center of the circle, and the negative r direction is going out, away from the center. So if we take the net force in the r direction, that should equal m times the acceleration in the r direction. And of course, the last step here is just to realize that the acceleration in the r direction is given by v squared over r. So this is typically how we deal with circular motion problems. Okay? The net force in the radial direction equals m v squared divided by r. Okay, so with that said, I think we're ready to do an example because we know how to deal with gravity and we know how to deal with circular motion, so it seems like we should be able to deal with a circular orbit. The International Space Station, ISS, is in a circular orbit around the Earth at an altitude of 408 kilometers above the surface. So that's how high off the ground this satellite is. The mass and the radius of the Earth are given here. The mass is 5.97 10 to the 24 kilograms. The radius is 6,370 kilometers. Question is, what is the orbital speed of the ISS? So how fast is it moving as it goes in a circle around the Earth? Okay, so we'll work this out. So the notation we're going to start using is, we'll have big M represent the more massive object. That's going to be the Earth in this case. And then we'll have little m represent the less massive object. That's going to be the space station. So the space station is in circular orbit around the Earth, just like this. And what's keeping it moving in a circle is some kind of force going in. Well, what's that force? It's gravity. The force of gravity acting on the space station is what pulls it in towards the center of the Earth and keeps it moving in a circle. Okay, so let's label a couple distances here. First, uppercase R, that's the radius of the Earth. So that's going from the center to the edge of the Earth, that's the radius. H, that's going to be what we call our altitude. So how high from the surface of the Earth is the satellite. Okay? Now, when we add these two together, we're going to get the distance called lowercase r, which basically is just the distance of the satellite from the center of the Earth. Okay, so here, let's do this. Distance of satellite to Earth's center is given by little r on the diagram, which is the radius of the Earth, big R, plus h, the altitude. So let's actually add these numbers. The radius of the Earth is 6,370 kilometers. The altitude is 408 kilometers, which gives us 6,778 kilometers with 3 sig. Now a kilometer is just 10 to the 3 meters, kilometers, 10 to the 3 meters. And so what we can say is, so 6,778 times 10 to the 3 is the same as 6.778 times 10 to the 6 meters. So this is an important number. We're going to refer to it a lot. This is the distance between the satellite and the center of the Earth. That's what we just found. Okay, so now what we're going to do is apply Newton's second law to the satellite, which says the net force in the radial direction is equal to the mass of the satellite times its acceleration in the radial direction. And so, well, the force is just gravity. That's the force pulling it in. And so we have, for the force of gravity, G, big M, little m, divided by lowercase r squared. So be careful about which radius you're using. In the last lecture, we found that if you have a spherical object, you can treat it as if all of the mass of that object is at the center. Okay? So basically what we have is a distance from the center of the object. That's what matters. So on the other side, we have the mass of the satellite, which is little m, and the acceleration is v squared divided by r. If you recall, the entire point of this problem is to figure out what v is. So let's work it out. Okay, let's first cancel out little m. That divides out. Then let's multiply through by r, which gives you just, instead of r squared on the bottom, just one factor of r on the bottom. So we have gm over r. That equals v squared. So v is going to be equal to square root gm over r. And that's something we can calculate. Okay, so g is this constant, 6.67, 10 to the minus 11 newtons, meters squared per kilogram squared. The mass of the Earth, big M, is 5.97, 10 to the 24 kilograms. And the distance between the satellite and the center of the Earth is equal to 6.778, 10 to the 6 meters. We'll have to square root that whole thing. And what do we get? Well, you should be getting 7,664 meters per second. Now, let's actually work out the units real quick, because when it comes to gravity, the units can get a little tricky. But the general idea is, if everything we plug in is in SI units, everything that comes out will be in SI units. So speed should be in meters per second if everything that we plug in is in SI units. But let me just show you why this works. Okay, so this is kind of a detour where we do an analysis of our units. Okay, so I have a square root. Over here I have newtons, meters squared over kilograms squared. That's my unit for big G. I also have kilograms on top from the mass of the Earth right there. And then I have meters on the bottom when I plug in the radius. Okay, so overall, I can cancel out a couple things. I have newtons. I have one factor of meters on top, because meters squared divided by meters gives me meters. I can cancel out one factor of kilograms, just have one factor of that on the bottom. And then that's under the radical, under the square root. The next thing is to remember that a newton is a kilogram meter per second squared. And again, that's coming along with meters over kilograms, all under the radical. We can cancel out kilograms. Two factors of meters on top is meters squared, and then we're dividing by seconds squared. This is meters per second. Okay, so that's why I was able to say that this comes out in meters per second. How about we do one more thing? Let's convert it to kilometers per second, because the question said give the answer in kilometers per second. So I have 7,664 meters over seconds. Okay, in every 1,000 meters, I have 1 kilometer. That's the conversion factor. So cancel out meters. Now we have kilometers per second. And so we get 7.66 kilometers per second when we round it off to the right number of sig figs. So I just want to point out that that's an absolutely ridiculous speed. It's moving really fast. Every second that passes, it moves almost 8 kilometers. Okay? There's pretty much nothing on Earth that you can think of that's moving that fast. Okay, so it's a truly extraordinary speed. And I have a follow-up. So given that we found the speed of the ISS in its orbit around the Earth, figure out the period. And remember what period means for circular motion. It's how long does it take to complete one full circle. Well, in the case of the ISS, that would be like asking, how long does it take to go around the Earth one time? All right? So think about your answer, pause the video, see what you get, and then come back to it. And by the way, we're going to give our answer in units of hours. So how many hours does it take to go around the Earth one time? Okay, so let's go through that. What I want us to do is think about the speed we just found as being the distance that the ISS travels over the time it takes to travel that distance. So v is equal to, let's set the distance equal to 2 pi r, meaning it's the circumference of this circle. If the distance is 2 pi r, that means it's traveled one full loop around this, in this orbit. And that means the time it takes is the period, because we travel one period every time we make one full circle. So to solve for the period, solve for t, we're going to have 2 pi r divided by v. And now we can just sort of plug and chug. So the period is 2 pi. Okay, what is the radius we found? How about we do it in kilometers? We found 6,778 kilometers. 6,778 kilometers. We need to divide that by the speed, and what we got was 7.664 kilometers per second. So units of kilometers cancel out, seconds goes to the top, and what we're left with is a time measured in seconds. So if you do the calculation, you should get 5,556 seconds. So again, that's not super useful because it's not really how we count time. At a certain point, we just say minutes or hours. So let's do 60 seconds in every minute. Okay, and then let's also do 60 minutes in every 1 hour to get the units to convert to hours. And this works out to, if you do the math, 1.543 hours, or 1.54 if we're just going to round off to 3 sig figs. Okay, so, I mean, really think about that for a second. If you've ever taken an international flight to a really distant country, like India or China, somewhere on the other side of the world, it takes a long time. Nowhere even close to an hour, right? We're not just talking about that. We're talking about going around the entire Earth one time in a full circle. And it only taking about 1.5 hours. So meaning, you're in the International Space Station, you put on a movie, typical comedy movie. By the time that movie is over, you've already gone around the Earth one time. Okay, so it's moving really, really fast. Okay, so we talked about circular orbits, and we did a couple calculations, so hopefully you can kind of see how if I give you a certain set of numbers, you can calculate the speed or a period of an orbit, given everything we've learned so far. But I do want to add a little bit of sort of real-world complication when it comes to circular orbits. Okay? And this takes us to something called orbital decay. Okay, so if we imagine something like the International Space Station orbiting the Earth, moving in a circle, we think to ourselves, is that just going to move in a circle forever? Is it just going to orbit forever? Or is the orbit going to change over time in some way? So what I want you to think about is the fact that Earth's atmosphere, if something is moving through the air, in other words, it experiences what we call a drag force, something we talked about back in chapter 5, right? There's a resistance to motion through the atmosphere. We call this a drag force. And we typically think of space as being completely empty, so there's no air or air resistance out in space, but that's not really the case. See, the Earth's atmosphere, as you go up in altitude, it gets thinner and thinner. So there's less and less atmosphere as you go up. But there's not really like a line where the atmosphere goes away, right? It just gradually thins out as you go up in altitude. And that means something like the International Space Station, even though it's several hundred miles up, it's still moving through a little bit of atmosphere, even at that incredible altitude. So that means there's a tiny little bit of a drag force acting on it as it orbits the Earth. What does a drag force do to something that's moving through the atmosphere? Well, it slows it down. And the effect of that is, gradually over time, any satellite is going to be slowed down due to this drag force. And as it slows down, it actually spirals in towards the Earth. Okay? So let me show you what that looks like in an animation. So gradually over time, the satellite is being slowed down by this drag force, and as that happens, it spirals in closer and closer to the Earth. Now you can imagine what the end point of this is. At some point, if this continues on, the satellite is going to crash into the Earth. And typically, we don't want that to happen. So, how do we prevent this, what we call orbital decay? Well, every so often, if you have a satellite in a sort of low Earth orbit like this, so pretty close to the Earth, you need to regularly boost it to prevent orbital decay, meaning you need a rocket to fire such that the satellite moves back to where it's supposed to be. Okay, and then it spirals in a little bit more, and then, okay, we got to boost it back to where it's supposed to be. So there's this regular correcting of orbits that happens for any real satellite in low Earth orbit. The math of orbital decay is pretty complicated. You need calculus to really do it right. So we're not going to get into that, but I just wanted to show you the concept in that the real world, there's orbital decay, and we have to correct for that. Okay. The next type of circular orbit that I want to talk about is something called a geostationary orbit. Okay, so a geostationary orbit is an orbit that moves around Earth's equator, and it has the exact same period as the rotation period of the Earth. So let's really think about what this means. If I have a satellite and it's in a geostationary orbit, its period is going to be 24 hours, because that's exactly how long it takes for the Earth to rotate one time. And if you think about what this means, okay, the satellite is moving around the Earth at exactly the same rate as the Earth is rotating, and that means from the perspective of someone on the ground, it looks like the satellite is just staying in a fixed position overhead. It looks like it's not even moving. So I don't know if you guys have ever taken a look at the night sky and seen a satellite go by, but typically the ones you can see real easily are moving really fast across the night sky. It's like they just come and go within a minute or so. In geostationary orbit, you're just going to see that satellite remain in the same place overhead. It looks like it's not moving. Why does this work? Well, take a look at the animation. So what's being shown here is, again, the rotation period of the Earth is exactly matching the orbital period of the satellite. So they're orbiting together, or they're rotating together, and wherever that satellite happens to be overhead, it's going to be staying there as time goes on. And sometimes we want this, right? Like, you might want a satellite that just stays right overhead so you can always communicate with it, rather than it going to the other side of the Earth where you can't easily communicate with it. Or maybe you want to take pictures of a certain spot on the Earth and just keep taking pictures of that same spot on the Earth. Again, you might want a geostationary orbit to make that happen. That's the idea. More information about that on this link. Okay, but the example that I want to go through is, what is the altitude, height above the surface, that you have to put a satellite so that it's in a geostationary orbit around the Earth? Okay? So we know the mass and the radius of the Earth from before. We're going to use those numbers. Okay, so let's work it out. So let's first think about the period, right? The period of a satellite, if it's in a geostationary orbit, is going to have to equal, well, 1 day, right? So it has to orbit the Earth in the exact same amount of time it takes for the Earth to rotate once, which is 1 day. So, okay, let's convert this to seconds, because eventually we're going to need everything in SI units, so let's just do that before we go any further. In 1 day, we have 24 hours. In 1 hour, we have 60 minutes. In 1 minute, We have 60 seconds, so let's do some unit cancellation. Days go away, hours go away, minutes go away, and then we're left with seconds. So this comes out to 86,400 seconds, which is just a day. Okay, next thing we'll do is apply Newton's second law to the satellite. Okay, so we have the net force in the radial direction equaling m times the acceleration in the radial direction. And just like before, we know that the force is gravity given by g big M little m over r squared. That's just how the force of gravity works. That's the law of universal gravitation, discovered by Newton. So then on the other side we have the mass of the satellite, which is little m, because big M is going to be the Earth, right? The acceleration, v squared divided by r. Cancel out the mass of the satellite, and here's what we have. Just like before, in the previous problem, we have v squared is equal to big G, big M divided by r. Okay, now let's think about the speed once again as being the distance traveled divided by the time, which, if we put this in equation form, is v is equal to 2 pi r. That's one circumference, that's the distance you travel, divided by capital T, that's the period. Again, this is just the idea that in one period, you travel one circumference. Okay, so with that, what we can do is take, 2 pi r divided by t, and sub that in for the speed, which in this equation is being squared, and equate that to big G, big M divided by r. Okay, so on the left-hand side, I have to square everything. So I'm going to get 4, I'm going to get pi squared, I'm going to get r squared divided by t squared. That equals gm divided by r. So my next move is I'm going to multiply on both sides by r, which gets rid of the r in the denominator here, and it makes this r to the third power. I'm going to multiply through by t squared, which gets rid of the t squared in the denominator, puts it over here. So on top, on the right side, we're going to have gm t squared. And then finally, I'm going to divide out the 4 pi squared. So what we have is r to the third power equals gm t squared over 4 pi squared. So what we're going to do is solve for r. We're interested in what the radius of this orbit is. So we're talking about the distance from the center of the Earth in particular. So if I have r to the third power, and I just want to solve for r, I have to get rid of that third power. Okay? That involves taking what we call the cubed root of both sides, but I like thinking of the cubed root as the 1/3 power. So if I take r cubed, here, let me just on the side say, if we take r cubed to the 1/3 power, we just get r. Okay? So I'm taking both sides to the 1/3 power, so I have r equals gm t squared over 4 pi squared to the 1/3 power. And that means r is equal to, now we can plug in the numbers. G is equal to 6.67, 10 to the minus 11, newtons meters squared per kilogram squared, those are the units. The mass, 5.97, 10 to the 24 kilograms. T is going to be 86,400 seconds, and we're going to square that because t is squared right there, and then divide that all by 4 pi squared, and then take that to the 1/3 power. So it's a lot to calculate, but if you put this into your calculator, here's what you're going to get. You're going to get 4.223 times 10 to the 7 meters. Okay, so let's make some sense out of that. We haven't actually answered the question because this is not the height above the surface. This is actually the distance to the center of the Earth. So let's draw this out. So the Earth is here. The radius is, we're going to call that radius uppercase R. And then h, that's going to be the height above the surface. And then when we add these two together, we get lowercase r, which is the distance from the center. So this is the circle we move in. Again, if I want to measure the radius of that circle, I have to take the entire distance to the center of the Earth, which means the r that we found, lowercase r, is equal to uppercase R, the radius of the Earth, plus the height above the surface. And I'm trying to find the height above the surface, so that's going to be little r minus big R. Okay, so what we found over here is distance of satellite to Earth's center. We're also given the radius of the Earth, which is 6,370 kilometers. That's actually the same as 6.37 10 to the 6 meters. That's Earth's radius. So apparently what I need to do to find h, the height above the surface of the Earth, is subtract these two numbers. So h is going to equal 4.223 10 to the 7 meters minus 6.37 10 to the 6 meters. So crunch those numbers, and what you come up with is 3.586 10 to the 7 meters, and we can round that to a nice 3.59, because we're going to have 3 sig figs at the end of this, 10 to the 7 meters. That's the height above the surface. So just to give you a sense of proportion, that is about 22,200 miles. So it's a really big height above the surface of the Earth to get this 24-hour orbital period. Remember that when you're really close to the surface, like with the International Space Station, the orbital periods are more like, a couple hours, 1.5, in that range. So to get to a really much longer 24-hour period, you have to go way, way further out. Okay, that's the idea. Okay, so that does it for geostationary orbits. The next thing we're going to do is we're going to calculate the mass of the Earth. Okay, so throughout this lecture I've been saying, oh yeah, the mass of the Earth is just, 5.97 10 to the 24 kilograms. How could I possibly know that? Okay, is there a way I can just sort of put the Earth on a scale and weigh it? No, but we can actually do something clever, which is we can use how objects orbit the Earth, study how objects orbit the Earth, to figure out how massive the Earth is. So I'm going to show you how this works. What we're going to do is use the orbit of the Moon around the Earth. Okay, we're going to assume the Moon is in a circular orbit around the Earth. And we know some information about that orbit. I think you'll recall that the distance to the Moon is about 3.8 times 10 to the 8 meters. And that's about 240,000 miles, for reference. And the period of the Moon's orbit around the Earth is about 27 days. And in seconds, that's about 2.4 10 to the 6. Okay, so in other words, this is the radius of the Moon's orbit right here. And this is the period, how long it takes for the Moon to go around the Earth one time. It's about 27 days. Okay, so what we're going to do is start with Newton's second law, just like before. And that is the net force equals mass times acceleration. And just so we're clear, I'm applying this to the Moon. Okay, I'm doing F equals ma to the Moon, which I'm calling little m, and the Earth is going to be big M. That's the notation. All right, so what do we have? Well, the force is the force of gravity, which is g big M little m divided by r squared. And on the other side, we have mass of the Moon, that's little m, times the acceleration, which, again, if it's moving in a circle around the Earth, is v squared divided by r. Okay, so basically the same thing we came up with for a circular orbit, but this time I'm not going to solve for v. Instead, I'm going to solve for big M. Okay, so we're going to start by canceling out little m. That drops out. We're going to multiply through on both sides by r squared, which gives us just one factor of r on top. And then I'm going to divide by g. So when it's all said and done, big M, that's the mass of the Earth, equals r times v squared divided by g. Well, I know r, and g is just a constant, which I'm using. And then if I would only know what v is, then I can figure out what the mass of the Earth is. If I could just figure out how fast the moon is moving, then I can figure out the mass of the Earth. So let's get the moon's orbital speed. Well, speed is distance over time, and as always, we can think of that speed as being 2 pi r, one whole circumference around the circle, divided by t, which is the period. Okay, so we can actually plug the numbers in for this. The radius is 3.8 10 to the 8 meters. So 2 pi r is 2 pi times 3.8 10 to the 8 meters. Divided by the period, that's 2.4 10 to the 6 seconds. Do this calculation, and you'll get 995 meters per second, which is the orbital speed of the moon. Okay, so we actually saw that in the previous lecture, just going through it again. Now, with all these numbers, with v, r, and g, all of those numbers known to us, we can calculate m, the mass of the Earth. So what am I doing here? I'm plugging in the radius of the moon's orbit in for r. So same as before, 3.8 10 to the 8. I'm plugging in v for the speed of the moon's orbit, 995 meters per second, and that's being squared. Dividing it all by g, which is 6.67 10 to the minus 11. The units are newtons meters squared over kilograms squared. Okay? So I don't want to go through the whole unit analysis here. It does turn out that this ends up being in kilograms because it's a mass, and it ends up being 6 times 10 to the 24 about if you do this calculation. Okay, so it's not a perfect calculation. There are a number of reasons for that. One is, as I said, the moon actually doesn't move in a perfect circle around the Earth. The shape is actually an ellipse, which is a little more complicated. But this gets us really close to the right answer. Okay? 6 times 10 to the 24 is really close to the right answer. So that's how you calculate Earth's mass. And so, with that said, it's not too much of a stretch to take what we just learned about and try to apply it to calculate the sun's mass. Okay? So, in the case of the sun, we have the Earth orbiting the sun every year, 365 days. And let's just say that we know the distance, and it's about 93 million miles on average. Changes a little bit because it's not a perfect circle, as I said. So, given all these numbers, let's estimate the mass of the sun. We're going to do exactly what we just did to estimate the mass of the Earth. We're going to apply it instead to estimate the mass of the sun. All right, so let's work this out. Okay, now the first thing I want to do here is get the period of Earth's orbit around the sun. Okay, well, that's pretty much the definition of what a year is. The time it takes for the Earth to go around the sun is a year. And what we want to do is take this period, t, and convert it to seconds, just like we did in the previous problem. So I have 1 year, 365 days. So right away, this is not even exactly correct. We're ignoring leap year, but that's a small correction. Let's just ignore it. Every 1 day has 24 hours. Every 1 hour has 60 minutes. And then every 1 minute has 60 seconds. So let's cancel out years, cancel out days, hours, minutes. Okay. So how many seconds does it take for the Earth to go around the Sun? It's 3.15 10 to the 7 seconds. Okay, so in other words, about 31 million and a half seconds is a year. Cool. Let's do something else with this. The radius of Earth's orbit is basically the distance between the Earth and the Sun, and we were told that it's about 93 million miles, or 150 million kilometers. Okay, so first of all, a million is 10 to the 6. So if I want to say 150 million, I could write this as 150 times 10 to the 6 kilometers. But hey, a kilometer is just 10 to the 3 meters. So I have 150 times 10 to the 6 times 10 to the 3 meters, or 1.5 10 to the 11 meters. So that's how many meters from the Sun that the Earth is on average. And the whole point of this is we can get the speed, the orbital speed of the Earth as it's moving around the Sun. So we have 2 pi r divided by t, just like before. Okay, we have 2 pi. This radius is 1.5 10 to the 11 meters. And the time it takes is 3.15 10 to the 7 seconds. Again, what we're saying here is it takes this many seconds to travel in one full circle around the Sun, and the speed is therefore going to have to be, if you calculate this, 2.99 10 to the 4th power meters per second. That's the speed of Earth's orbit. So that's an absolutely ridiculous speed. Very, very large. Okay, the next thing I'm going to do here is apply Newton's second law. To the Earth. So remember the sort of strategy here. We have a big M, which is the Sun, and then we have a little m, which is going around the Sun, which is the Earth. So we take the net force in the radial direction, we get m times the acceleration in the radial direction, which gives us the force is gravity, big G, big M times little m. Again, we just need the product of the two masses upstairs, divided by r squared, equals m. Our acceleration is v squared divided by r. Now, the whole point of this is we can cancel out little m, which is the mass of the Earth, and then we can solve for big M, which is the mass of the Sun, and just like before, that's going to end up being v squared times r divided by big G. Okay, so if you cancel everything out, and you solve for big M, you're going to get v squared times r divided by g, which in this case gives us our orbital speed is 2.99 10 to the 4 meters per second, and we'll square it. Our radius is 1.5 10 to the 11 meters, and then our g is 6.67 10 to the minus 11 newtons meters squared per kilogram squared. And what does that equal? Well, if you do the calculation, you're going to get 2.0 times 10 to the 30 kilograms. And again, this is really, really close to the right answer. I think the actual mass is like 1.99 10 to the 30 kilograms. And if we compare this to the mass of the Earth, okay, so here, this is for the Sun. For the Earth, again, we have about 6 times 10 to the 24. So the Sun is about 300,000 times more massive than the Earth. About 300,000 times more massive than the Earth. All right, so that's circular orbits. And I think we've said enough about that, so we can go on to the next topic, which is gravity near Earth's surface. And so one thing we're going to get in this section of the lecture is an understanding of why is it that near Earth's surface things accelerate down at 9.8 meters per second squared. We're going to finally understand that fact and why it's true. So, in fact, we're not just going to get a way of doing this for the Earth. We're going to be able to do this for any kind of spherical body. Okay, so lowercase g, when we've seen it in our physics equations, remember what it means. It's the acceleration of an object in free fall near the surface of some kind of spherical body. We're usually talking about the Earth, in which case g is 9.8 meters per second squared. But keep in mind, we could think about this problem more generally in terms of, let's say, the planet Mars. Okay? Maybe I want to know what the value of g is on the planet Mars. Or I want to know what the value of g is on a different planet, like Venus. Right? We can really just talk about this generally. So the general problem of a small object, mass little m, which is really close to the surface of a large spherical object, mass big M, and it's in free fall. Okay, so to be clear, this is an example of that problem. This is my little m, my small mass is the pencil, the Earth itself is my big M, and the pencil is in free fall near the surface of the Earth. That's the general problem we're talking about. All right? So, let's take Newton's second law and apply it to the small mass. This says the net force acting on that small mass is equal to its mass times its acceleration. Now, if we're in free fall, that means the only force that's acting on the object is gravity. That's the definition of free fall. So, how do we think about the force of gravity acting on this object? Well, it depends on how far from the center of the big mass we are. But if we're staying really close to the surface, okay, maybe only going up a couple of kilometers off the surface, you know, the distance from the center is not going to be that different from just the radius of the Earth. Because, I mean, think about this. The radius of the Earth is about 6,000 kilometers, around there. So even if I'm standing on top of Mount Everest, okay, I'm really not that much further from the center of the Earth as I would be if I'm standing at sea level, right? So we're going to say that the distance from the center of the Earth is basically just the radius of the object. And if we go off, you know, some height above the surface, it's really not going to change that much. Okay, so for the force we have big G, big M times little m, again, product of the two masses, divided by the separation, which capital R is going to represent the radius of the object, so that's what we have. Divided by r squared. On the other side, when we have mass times acceleration, I'm going to plug in for the acceleration g, because g is just a special case of acceleration, right? It's just the name we give to acceleration when something is in free fall. So just plug in g for that. And it's really simple, just cancel out little m, goes away, and what we get is the free fall acceleration is given by big G, big M divided by r squared. So, if I have a spherical object, okay, it can be a planet, it can be a moon, it can be a star, whatever the case may be, and I'm right on the surface of that object, just like right now I'm standing on the surface of the Earth, the free fall acceleration is going to depend on only the mass of that object and the radius of that object. That's all that matters, is the mass and the radius. Okay. So let's do the calculation for Earth, because by now we know the mass of the Earth. We have a good reason to justify why we know the mass of the Earth. And we know the radius. And all we have to do to calculate the free fall acceleration on Earth is plug in the mass and the radius. Okay. So for the radius, we have 6.4 times 10 to the 6 meters. For the mass, we have 6.0 10 to the 24 kilograms. And for big G, which is the universal gravitational constant, as always, we have 6.67 10 to the minus 11. So plug all that in. And what do we get? So take some time at home to actually do this calculation. See, this is how it comes out. Well, the number we get is 9.8, which is looking pretty good. let's think about units for a second here. So it looks like I've got kilograms upstairs and then kilograms squared on the bottom. So cancel out one factor, we have kilograms on the bottom. It looks like I have meters squared on top and then also meters squared on the bottom, so those cancel. All I'm left with is newtons divided by kilograms. All right, so just remember that a newton is a kilogram meter per second squared, which allows you to cancel out kilograms. And we get 9.8 meters per second squared. That's where it comes from. We just know the mass and the radius of the Earth. We can calculate that g, lowercase g, is equal to 9.8 meters per second squared. That's where it comes from. Okay, so moving on. So now that we know that we can generally calculate the free fall acceleration due to gravity on any object, any planet or moon, you can make this calculation for, let's say, Mercury. And you'll find that the value of lowercase g is only 3.59 meters per second squared. So basically, if I'm standing on the surface of the planet Mercury and I drop something, well, it's going to fall down a lot more slowly than on Earth. So it's almost like gravity is much weaker on the surface of Mercury. If I look at Venus, it's actually really close to the value on Earth, only a little bit less, 8.87 meters per second squared. Okay, so Venus is almost the same size as Earth, and that's why it's pretty close in its value of g. If we go to a planet like Jupiter, absolutely ridiculous gravity there. 25.95 meters per second squared. And then if we go to Pluto, which is actually not even a planet, but let's put it on the list anyway, gravity is pretty pathetic, right? Only 0.4 meters per second squared. And again, all of these can be calculated using that formula that we just came up with. So I want you to try this out. So given that the planet Mars has a mass of 6.39 10 to the 23rd power kilograms, so about 10 times less than Earth, and a radius of 3,390 kilometers, estimate the value of g, lowercase g, free fall acceleration, at the surface of Mars. So quite literally this means if you're standing on Mars, you drop something, how fast does it accelerate? Then as a follow-up, estimate the value of g if we're 1,750 kilometers above the surface. So now we're not just standing right here, we're above the surface. What's the free fall acceleration in that case? Okay, so let's work both of these out. And so, without having to sort of reinvent the wheel and rederive the equation, we know that at the surface of Mars, that g is going to be equal to big G, big M, divided by r squared. So again, that's the mass of Mars, that's the radius of Mars. And let's just plug in what we have. We have 6.67, 10 to the minus 11, minus 11 newtons meters squared per kilogram squared. The mass is 6.39, 10 to the 23 kilograms. Now the radius is 3,390 kilometers, but we want this in meters. So that's 10 to the 3 meters for a kilometer. And we have to square it. Okay, so do the math. You get 3.71 meters per second squared. So, of course, gravity, because Mars is a smaller planet, is a little bit weaker than on Earth, right? Or a lot weaker in that case. Okay, the follow-up said, what is the value of g at an altitude of 1,750 kilometers above the surface? Okay, so the same basic formula applies, except we're not just going to use the radius of Mars, we're going to have to add this distance to our radius, because now we're further away from the center of Mars than we were before. So we have 6.67, 10 to the minus 11. I'm going to leave off the units here. You know what they are. 6.39, 10 to the 23, again, just the same old constant g and then mass, and then divide by, okay, so now what I'm going to do is I'm going to take 3,390, add to that 1,750, that's how many kilometers we have, but in meters, we would take that and multiply by 10 to the 3, and then we would square that because, of course, we have to square the r. Okay, so basically, when you go a substantial height above the surface, you have to add that height for your r. Okay, so the next thing is get a number out. Crunch the numbers, you get about 1.61 meters per second squared. And this is exactly what we expect because as you're getting further and further away from the surface of Mars, you'd expect gravity to be getting weaker and weaker, and that's exactly what's happening. Okay? So that's how this works. And, okay, moving on to the next thing. So everything we've said so far about how to calculate freefall acceleration, it's a little bit idealized. It's a little bit of a simplified version of the reality, which is that g is not uniform over the surface of the Earth. Okay? In other words, 9.8 meters per second squared, you want to think of that as like an average. But it actually varies a little bit, it changes a little bit from place to place on the Earth, and there are a number of reasons for that, which I want to get into right now. Okay, so the first reason that g is not uniform is that the Earth isn't even a perfect sphere. Okay? We've been treating all these, in these different derivations, we've been treating it as if we have a perfectly spherical object, but that's not really the case. For one, the Earth has mountains and valleys, okay? And it also bulges out at the equator. Okay, let me actually show you what this means. So this is what the Earth would look like if it were not rotating. Okay, it wouldn't be any like fatter at the equator than it is at the poles. Looks pretty much spherical. But since the Earth is rotating, like any rotating object, it bulges out at the equator. And in fact, you get this. So it's not a perfect sphere by any stretch. Okay. The next thing is the Earth is rotating on its axis. Okay. So I gave you some sense back in chapter 4 that when you're on a rotating frame of reference, the physics gets a little complicated, and that's point number 2. Okay, the fact that the Earth is rotating is going to affect gravity in subtle ways. And then the last thing is the composition of the Earth is not uniform. Meaning, look, it's not like the Earth is just made out of one substance all over, right? We have oceans, we have land, and even if you dig into the Earth, right, you may see that there's a mineral deposit or an oil deposit beneath your feet, okay? These things can have different densities, which leads to slight changes in the strength of gravity from place to place. So for instance, if I'm standing right on top of something really, really dense, gravity is going to be a little bit stronger in that region. And if I'm standing on top of something that is less dense, then gravity is going to be weaker in that region. And in fact, it doesn't have a big effect. It's a really tiny effect, but you can measure it. And this is, in part, how people figure out that there's a valuable resource underground. You look for slight changes in gravity from place to place to hint at you that there's something underneath the ground that you might want to dig up. Okay? So, the reality is g is not uniform. It's a little more complicated than that. So we're going to do a couple problems here which deal with this issue of g not being uniform. And so this says that the strength of Earth's gravity decreases with height. Right? It gets weaker and weaker as you get further and further away from the Earth. So what I want you guys to do is estimate the value of g at the top of Mount Everest, which has a peak height of 8.848 kilometers above sea level. So when you do this calculation, I want you to assume that the Earth is basically a perfect sphere. with just some mountains and valleys sitting on top of it. Okay? So the radius of that perfect sphere would be 6,371 kilometers. And then of course we know the mass of the Earth, which I'm going to give you to high precision, 5.972, 10 to the 4 kilograms. 10 to the 24 kilograms. Okay? Okay, so pause the video, try to work this out, and then we'll come back to it. Okay, so here we go. So the picture that you should be thinking here is we've got a perfectly spherical Earth, but we just have Mount Everest peeking out above that otherwise perfect sphere, and you're standing up here on top of Mount Everest. Now, the height of Mount Everest, that would be, from sea level to the top, let's call that h. And then the radius of the Earth, we can call that uppercase R. So the idea is, since you're a little bit further away from the center of the Earth when you're standing on top of Mount Everest, compared to if you were standing at sea level, then g should have a smaller value, slightly smaller value than before. And okay, if g is equal to big G, big M, divided by r squared, in this case for the radius, your distance from the center, we're going to want to use the radius of the Earth plus the height, and then we'll square that. Right? So it's just a modified version where we add that extra height into our equation. And so, here's what we get. 6.67, 10 to the minus 11, newtons meters squared per kilogram squared, times the mass of the Earth, 5.972, 10 to the 24 kilograms, divide out. Okay, so now what we're going to do is we're going to add 6,371 kilometers, that's the radius, plus the height of Mount Everest, which is 8.848, that's kilometers. We want to get this in meters, so we're going to take that and multiply by 10 to the 3. That gives us meters. And then we have to square that whole thing. That's the calculation we need to do. And when you do that calculation, you get 9.786 meters per second squared. So, in other words, gravity is slightly weaker on Mount Everest, on the top of Mount Everest. So, I'm sure that, I'm standing at sea level, I can't dunk a basketball, but if I were standing up here, I'm sure I'd be able to dunk a basketball because gravity's a little weaker, right? Well, it's only a tiny bit weaker. If you do the calculation, it's only about 0.2% weaker than at sea level. So that's what I want to highlight. There are these slight changes in the strength of gravity from place to place, but they're really small changes. They're not really that significant. Only like 0.2%. Okay. So I think we're going to end with this one, which is getting into the effects of Earth's rotation. And so I want you to think about this. So let's say you're standing on a scale at Earth's equator. Okay? So maybe you live in like Brazil, somewhere like that, that's right at the equator. All right? So, typically you would say, well, I'm not moving, I don't feel like I'm moving, but in fact, you're moving in a circle because you're on the rotating Earth, which means you are accelerating. Anything moving in a circle must be accelerating. So you're on the rotating Earth at the equator, you must be accelerating. In which direction? Well, towards the center of that circle. So your acceleration is going to be going in towards the center of the circle, which means the net force acting on your body is going in towards the center of that circle. All right, so let's kind of make some sense out of this. If you're standing on this scale, what is the direction of the force of gravity? Well, you're being pulled in towards the center of the Earth with a force, we'll call it Fg. Okay, that's not it, because you're standing on scale, which provides a normal force going this way. But notice how they're not just equal, they don't just cancel each other out. The overall net force is going inwards. Okay? Now, remember from chapter 5, or no, it was actually chapter 4, that when you're standing on a scale, all that the scale is telling you is the normal force. It's really not directly measuring gravity, it's just measuring that normal force. So in fact, if you're at the equator, you're going to be a little bit lighter, because that normal force is going to be a little bit smaller than if you were, let's say, standing at the North Pole or the South Pole. By how much? About 0.3%. Okay, so let me show you how this works. The idea is you're thinking about someone on the rotating Earth, rotating like this, standing at the equator, like this, on a scale. And there is the radius of the Earth right there. We're going to use that eventually. Now, we're going to apply Newton's second law to this person, where the net force in the radial direction equals mass times acceleration in the radial direction. And let's just label those two forces. Of course, we have the normal force pushing outwards from the scale, and then we have the gravitational force pulling inwards, like this. And so these aren't equal because we are accelerating, right? If we weren't accelerating, we'd just have a balance of forces, and the normal force would just equal the force of gravity. But in this case, here's how it works. Now the force of gravity, that's going to be positive because it's going in towards the center of the circle. The normal force is going to be negative because that's going out away from the center of the circle. And the result is m times v squared divided by r. Well, the force of gravity is just m times g. You can think of it that way. And the normal force is just Fn. And that's equal to mv squared over r. We're going to solve for Fn by adding it to both sides and subtracting mv squared over r from both sides. So Fn is mg minus mv squared over r. Now, what this is telling you is the normal force, which is actually what the scale reads, is the normal force, is a little bit less than mg. It's mg minus v squared over r. Okay, so let's actually think about this. There's a percent difference we can calculate between this normal force and m times g. So the way this works is we're going to take this normal force, which is mg minus mv squared over r. We're going to subtract mg, so that's the difference between these two things I'm comparing. Divide out m times g, and then multiply 100. Okay, so what do we have? mg minus mg, those cancel out. On top we have mv squared over r. On the bottom, sorry, minus mv squared over r. On the bottom, mg. Cancel out the m's, times 100. Here's what we need to calculate, okay? Minus v squared over gr times 100. So if I calculate that, I'll know the percent difference between mg and the normal force that I feel if I'm at the equator like this. And it's a slight difference, but it's something to calculate. Okay, so first, let's think about the speed of the person. That's v right here. Well, like any other object moving in a circle, you can think of the speed as the circumference, 2 pi r, divided by the period, capital T. Now, we can put a number to this. 2 pi times the radius is 6.37 10 to the 6 meters. That's the radius of Earth. We've seen that number before. The period would be a day, but as we saw in a previous problem, we can take a day and convert that to 86,400 seconds. Okay, so that's the speed of the person. And then again, that's just one day. So the speed is, if you work it out, 436 meters per second. So that's how fast you're moving if you're at the equator. Okay? And notice that, let's say you're at the poles, like the North or the South Pole, your V is actually 0 because you're only moving if you're off of the axis of rotation. Anyway, so what's that percent difference? Now we can calculate it. So we have minus 436 meters per second squared, that's V squared, divided by G. Let's use 9.8. Okay, that's sort of the average value. And then the radius also is downstairs at 6.37 10 to the 6 meters, and then we'll multiply by 100. Okay, so the percent difference we're seeing here is about negative 0.3%. So, what is that telling us? If you stand on a scale at the equator, and then you fly to the North Pole, and you weigh yourself standing here, it's not going to give you the same exact answer. The difference will be about 0.3%, and you're going to be measured a little bit lighter if you're at the equator. Okay, that's the idea. So I think we can call it a day, and the next time we have a video, we're going to wrap up chapter 6, and we're going to talk about a couple things. Kepler's laws of planetary motion, and then some modern ideas of gravity. So everything we're talking about here is about, over 300 years old. So what's happened since then? What are some of the more modern concepts of gravity since Newton? So that'll be for next time. I'll see you then.